Okay. Hi everyone. Welcome to Peru Youth. This is our first hangout on air, and today our guest is Duncan DeVore, who is going to talk about introduction to Lagom, which is mostly a new open source project and is behind Lightbend. Welcome, Duncan.
Thank you.
So, Duncan DeVore is a software engineer on the monitoring team at Lightbend. Duncan believes in responsible design through functional programming with an abundance of test coverage. He loves to code, present, and help others work through the challenge of distributed computing. Duncan's open source projects include journals for Eventsourced and Akka-Persistence based on theory of Eventsourcing and CQRS. Okay, Duncan, you can start. Duncan, are you there?
Yep, can you hear me okay?
Yep, you can start, please.
Okay. My name is Duncan. I'm from Lightbend, and I'm going to talk tonight about doing microservices with our framework in particular, which is called Lagom. So let's get started. So at Lightbend, we have, over the last several years, been designing toolkits primarily focused on things regarding distributed systems. That's our primary area. And in doing such, we've learned quite a bit. One of our primary tools, obviously, being Scala. From a programming perspective, it's designed to be a scalable language. And our other being Akka, which is our toolkit for building distributed applications. And one of the things that we've learned over the years is that while these toolkits are great and they provide a lot of features and functionality to build distributed systems, building distributed systems is still a challenging endeavor. And so we set out to provide additional tools and resources that can kind of, make that that process from going from what we consider to be normal monolithic applications to distributed applications a little easier. And the one that we're going to talk about tonight is Lagom. So one of the key things is behind any good product or behind any good effort is to come up with a cool name. And a lot of our names are Swedish. This one in particular is Swedish, and it's Lagom is how you pronounce it. And the idea behind it is it's just right. It's not too much, it's not too little, it's sufficient, it's adequate, if you will. And there's a really good video here in the link that you can go forward when you get a chance and check out. It has to do with dairy products and milk, not programming, but it's a neat understanding of what the word Lagom means. And so our effort here is to provide a toolkit or a structure by which you can go ahead and build these types of things. That being said, Lagom is opinionated, and it has a specific idea in mind of how it should be done. So it's kind of structure based, and we'll see that as we get through the presentation tonight. So what we're going to do, our agenda tonight is going to be first an overview of the notion behind reactive. We'll then discuss why Lagom. We'll walk through Lagom from a development environment perspective, and then we'll also talk about two important aspects behind Lagom, one being the service API and the other being the persistence API. And then we will discuss production scenarios with Lagom. So the first one is reactive. When doing these types of presentations, especially remotely, sometimes it's difficult to get a sense of where the audience's experience level is. Oops, went back one. Where the experience level is. So I'm going to make the assumption that we have a mix of folks in the audience that have worked with distributed systems and some who don't or have not. And so it's important then to kind of go over some of these tenets that underlie it. So at Lightbend, our CTO, Jonas, was kind of like the leading driver, Jonas and Victor and some others who were not part of Lightbend, to come up with this idea of the Reactive Manifesto. And the Reactive Manifesto essentially is a document that lays out a philosophy and says, hey, if we're going to build these types of systems, what are the ideas? What are the brain dumps? What are some of the context behind this that can help us understand? We believe that with any solution that you build, there should be some type of underlying idea that makes sense and that is relatively easy to grasp. And building distributed systems are no different. So we have the notion of the reactive concept in the Reactive Manifesto, and you'll see 4 blocks here. Responsive, elastic, resilient, and message-driven. The top block is customer-focused or customer-centric. And the idea is that we need to be able to respond regardless of our situation. We don't want to be in a scenario where we don't respond. That's one of the primary challenges behind human relationships, where people do not respond to each other and then assumptions are made. And that always leads us down the wrong path. So the idea is, if we're having if we're struggling with load, if we're struggling with scalability, something along these lines, we want to be able to let the customer know. Otherwise, the customer will assume you're not listening and move on. And so that's why responsive is at the top. The 2 pillars that hold up responsiveness are elasticity and resilience. And the idea there is, in order to be able to respond at all times, I have to be able to flex or be elastic, or what we a lot of times traditionally call scale, in and out or up and down, so that in the event of increased load, I can scale horizontally, or if it's in the event of increased processing, I can scale vertically. And then in the event of failure, I can be resilient, I can recover. So those are the 2 primary pillars that support your ability to respond. You'll also notice there's an arrow where they point back and forth to each other. They're kind of like siblings. They not only support responsiveness, but they also support each other. So one of the ways that we can handle faults or errors is we can scale, and we can essentially add additional resources to our application that allows us to deal with those faults. So if a load becomes too heavy and things start to fail, then we can scale horizontally or vertically, depending on what the type of load is. In order to do this, the key component, or the base, if you will, is message-driven. Now, one of the things that's important is sometimes you'll see in documentation something called event-driven in concert with the idea of being reactive. It's not really event-driven. We view events as a significantly different component, and I'll talk about that a little bit later. But the idea here is loose coupling. The components in my system that are going to be elastic or are going to be resilient have some features about them that are crucial. And one of them is they're isolated. So if they fail, it's just them failing, not the entire system, etc. And they're also kind of like self-sufficient, if you will. And in order to do that, they have to be loosely coupled. So the idea behind that is message driven, and that's where things like Akka and actor systems that are designed to send messages back and forth, but the transport from a programmatic level is not baked into, if you will, each individual component. So they can essentially send a message and not really worry about how it gets to the other, or it gets to the recipient. This is very much like our like a post office, or even email, if you will, where you send a message to somebody and you don't know if they've read it yet or if they've received it yet. You won't know until they respond back to you. So the idea here is this loose coupling supports elasticity and resilience, which ultimately allows us to be responsive. So Lagom, or Lagom, why? Well, in setting out to essentially tackle this, one of the decisions that was made was there was a way that these types of architecture should be built, especially in relationship with microservices. So Lagom is opinionated on how a microservice should be built and how that microservice should adhere to the notion of the reactive manifesto, or being reactive. As a result, Lagom uses Lightbend technologies. It uses Play and it uses Akka. And the key there is that it is non-blocking and it is asynchronous. Those are two key components that are crucial in distributed computing. The idea here is if you're blocking, especially if you're blocking a thread, then that entire context in which you're trying to operate is now unavailable to anybody else that might want to use it. Furthermore, you've basically shut down that line of communication until you stop blocking, so you cannot send your message or interact with somebody that's in a remote environment either. So everything is non-blocking, everything is asynchronous. And additionally, in this opinionated vein, Lagom advocates for things like CQRS, command query responsibility, segregation, and event sourcing. The notion behind that is that these types of structures for storing data and processing, essentially reads and writes, are very distributed centric in their philosophies. And we'll talk a little bit more about that later in the presentation as well. The other thing is in building microservices in general, building a small application or one microservice is generally easy. The challenge becomes when you're building a system that has many microservices. So a lot of the existing frameworks out there today, and they're changing, I think, as a result of some of the work that we're doing, and just the industry beginning to realize the importance of this type of stuff. But they help you focus on building one particular microservice. Where they break down in many cases is the connection between the microservices. So Lagom, when we designed it, set out to really handle that issue. Another thing which is important was the development experience. If you use Play, there's some neat features behind it where you can essentially make a change and everything recompiles on the fly and then you can see it. When you're doing an Akka application, that's not the case. And so the development experience that we wanted to have for the developer was one in which if they make a change, that they can pick it up by automatic recompilation. And so that implies a build tool is kind of baked into the development environment. And also, we wanted to be able to have simple commands where the developer could spin the entire environment up with like one particular command, and that would spin up all the different microservices. It would spin up the storage mechanism, etc. On their development machine. They could get the thing set up and installed and running in a relatively quick manner. So those were all very important. And then the last piece was the production environment, where Lagom is intended to take you through production deployment and so forth. And these components, building microservices, the experience for the developer, and the production environment are important to the tool selection And we wanted to make sure that all of those were part of Lagom as a package. So, as I had mentioned, the intra-service communications are not brittle, and the communication just works. So, some of the key features of Lagom. Under the hood, it uses Play 2.5 and Akka 2.4. If you're familiar with those technologies, one of the key things is in Akka 2.4, you have things like clustering, which provide distribution management out of the box. You have streams, which essentially address the issue of back pressure, and you have persistence in the form of event sourcing and Akka-Persistence, which we'll talk about again, as I mentioned a little bit later. The other thing you get is SBT is the build tool. So you have this environment of which you can set up your application, and it's honed towards providing this developer experience. Cassandra is the default store for data storage. It's a very popular NoSQL database, and is pretty good at scaling. And Jackson for serialization, and Juice for dependency injection. So some of the technologies you get out of the box under the hood in Lagom. Now, the anatomy of a project is, as we see here, essentially, and this is one of the things that I particularly liked about Lagom. When I first saw the way Lagom was designed, I come from an Akka background, building distributed systems, some pretty large ones, and I'm an advocate for event sourcing and CQRS. And when I first saw Lagom, one of the things that stood out to me was the API and implementation explicit definition of those two concepts. And we talk about this in development and in Java and everything. We have interfaces and so forth. But a lot of times, as we build systems, those two concepts become mushed together, and we forget to create a explicit distinction. In Lagom, you have to. There's no other way to do it. So you have to define an API. You have to define an implementation. And I just really like that, I guess, opinionated aspect of it, because it makes it very explicit. You also have your traditional SBT stuff. You can have plugins. And there's a Lagom plugin that makes it real easy to get things set up. And also, obviously, your build SBT and such. If you're not familiar with SBT, the build SBT is kind of like the root build configuration. So, first thing we'll take a look at is our service API. So here's some code that gives you an idea of when you're writing a Lagom application and you're going to create your API. You're essentially, you can kind of think of this as like an interface, if you will, at actually what it is in Java. And so we have a abstract service that you'll extend, and you'll create your service. Now in the service, you're going to implement what we call a descriptor method. And it's essentially a set of endpoints. So for each endpoint that you have, you'll add a descriptor. And it's coupled with metadata of how the service is going to be called and how the service is going to be served. And in this particular case, we have one called Hello Service. It's going to be used by services to discover each other's location, is the idea under the covers, and it will allow for communication back and forth between the different services. So one service called hello, in which we will turn and invoke the say hello method, and we'll see that as you see right there, return named with calls, and there you see this say hello. So it lays out this idea of an API, which allows you to define your service abstractly. So then when you do your implementation, obviously, as long as you don't break the public API, your implementation is essentially encapsulated. And then you'll have a REST call and so forth. That's what it's using under the hood. Now, the service call in and of itself, essentially the service call takes a request and it will return a response. And you'll see their completion stage if you're familiar with futures. The idea, again, is this is asynchronous, it's non-blocking. So when the API returns a promise, that value might not be completed yet, but the API's promise essentially is that at some point in the future, you will get a response back. Since the value that you're going to receive back may not be computed as of yet, you can't act or interact with it immediately. So what you'll do is you can attach callbacks, and you're going to essentially transform your promise to a promise of a new value, and then you're going to essentially apply a composition method to it. So if you're not familiar with composing futures, this might be a little bit scary or a little bit confusing, but this is a pretty common pattern in dealing with this type of stuff, so you're non-blocking, which is crucial to your applications, not only its ability to scale, but also its ability to be resilient. And this whole thing gives you the ability to be asynchronous, which is ultimately what we're going after here. The other thing is messages are buffered into memory. So when you have a descriptor and you have a distinct message, that message itself for expedition purposes or to expedite, so you're not having to persist to disk or stuff like that, it will be essentially cached is what's going on there. So it makes it very efficient. Lagom also streams messages with Akka streaming under the covers, and this is an important concept as well. And streaming, I think, sometimes gets confused with what its real purpose is. So I'll speak to Akka streaming here. The primary purpose behind Akka streaming is pressure management. If you think of a sink, and you think of a faucet, and the faucet is pouring water into the sink. If the sink starts to fill up, a lot of times we would say, okay, we want to handle overflow, so how are we going to do that? Well, we'll put a second sink in. So now we have two sinks, and if the first sink fills up, it'll overflow into the second sink. And a lot of people view that as backflow or, you know, pressure management, and it really isn't. What that really is just queuing. In a true management situation where you're going to manage back pressure, it would be a scenario where the sink would actually talk to the faucet and it would say, hey, you are filling me up too fast, slow down. And the faucet would respond, okay, I'll slow down. And that's what Akka streaming does, or the streams API. It actually manages back pressure asynchronously, and essentially gives the sender essentially a notification to slow down. The sender, being part of that connection, will respond and say, okay, no problem, I will slow down. And that's true back pressure management. So in this particular situation, WebSockets are used because we have an HTTP layer, whereas in traditional Akka, you don't have to worry about that per se. So that's used as the transport protocol. So the next part is the actual implementation of your service. And as a reminder, this was the essentially the interface of our service, the API, where we had hello service as one of our descriptors. And now we'll see the actual implementation. So under the covers, we see the implementation, and it follows Java naming conventions here with hello service simple. And it implements an abstraction called hello service. And essentially, it's going to return this name in the form of a completed future. And that completed future is essentially going to be a string plus whatever the name is. So the key here to realize is that the invocation of say hello itself does not execute the call. It only returns the call to be executed. And that's, excuse me, that's one of the key things in dealing with futures here. So essentially, you're getting back a promise that you're going to get a response. And the advantage of that is, especially when you're going across asynchronous boundaries, or even not, you're cutting across different concerns such as authentication and so forth, you can begin to compose these ideas. And composition is real important because, you know, the individual pieces that you're trying to put together may not necessarily be dependent on one another. They may be dependent on one another for the final answer, but the actual fetching of the answer of each of your components may not be dependent on one another. So for example, if let's say I have some kind of strange question that gets asked, and there's three components to that question. One is, what is the current weather? What is the current stock price for Apple? And you know, what is the price of tea in Peru? Those are three questions. And when I get the answer to those three questions, I can then order them appropriately and respond back with a single answer. However, asking those three questions, they're completely independent, and I don't want to wait on finding out what the current weather is because I first asked what is the current stock price of Apple. So they can be asked asynchronously, and they'll all come back, and when they all come back, I can review them and then compose my answer together. And that's the idea. That's a crucial concept in distributed computing. And so with Lagom, you can kind of compose those answers back together because you're wrapping these things in futures. And here's the service or registering the service implementation, which is something else you do, is you essentially have an injection where you will bind your service, and you're essentially declaring the API and the implementation. And then you're registering these services together. So as you receive the request in, everything is properly routed. So a lot of these concepts under the covers can be somewhat complicated, but there's an abstraction here with Lagom that kind of makes it easy and lets the tooling fall through to the underlying architecture. When you create a module in your configuration, you essentially basically say, okay, here's my module, hello impl, hello module, and then execute or add it as an enable play module, and then it'll spin up. So again, driven by configuration in that sense. It's a very powerful mechanism. So the next piece is the persistence API. And the persistence API is built on top of a couple different principles. The first one is that each service has its own data. Now, in the development environment, that means that each microservice is going to have its own instance of Cassandra running. And that's driven by configuration as well. When you go to production, you'll most likely, you would have a distributed version of Cassandra and so forth. But in the development environment, each microservice is going to have its own service and has direct access to that database, and being Cassandra. And we also advocate event sourcing and CQRS. The idea here is with event sourcing, we're going to capture state changes, and we're going to essentially persist them as events. And in CQRS, we're going to separate the idea of writes and reads. And we'll talk about that more, I believe, on the next slide. Yeah. So CQRS, I have it underlined there, commands query responsibility segregation. Greg Young is kind of like the mastermind behind this. And it comes from another thing called CQS, which was command query separation. And essentially, the idea is in CQS, you would have one object which had different methods, one for reading and one for writing. CQRS takes that an extra step and says, instead of just having one object, we're going to have two separate objects. And one is going to be for writing, and one is going to be for reading. And the reason behind that is because there's a mismatch between your reads and your writes. Almost in no circumstances does a system read and write at the same frequency. So they should be able to be optimized independent of one another. The same pipe should not be used for both reading and writing. They should be separate. And that gives us the notion of commands and events. And a command in CQRS is any method that mutates state, or really requests to mutate state. A command can be rejected. Once that command has been accepted, that command would be turned into one or more events and then persisted. Once it's persisted as an event, it can never change because it's a historical recording of something that happened, is the idea. And so what that ends up being, as we talk about event sourcing here in a minute, is it ends up being a series of events that you record information. So therefore, a delete no longer is a delete. It's simply a new event. And we have a good example here to kind of explain that in better detail. So event sourcing is capturing of things that have occurred, as I had mentioned earlier, events historical in nature. And implicit into that design is you begin to, depending on the granularity of your events, you begin to capture behavior. And this has some really fascinating side effects on the business, let alone IT. So the other aspect about it is you're, as I had mentioned, you take a valid command that comes in. A command comes in, a request to do something. You validate it, and then you can take that command and turn it into one or more events. The key thing to understand that is that current state is not persisted, it is derived. And here's where the icing on the cake is. It ends up being an append-only store. So when you look at distributed systems, especially systems that are sharded, the notion of write-only or append-only is what I actually mean, is a much easier structure to persist in a distributed environment. The key is easier. You don't have compound or complex keys. You're essentially working on some type of hash, and that's a much easier key to distribute. So in your database, Cassandra, for example, you can now shard and do things like that. And it's a much easier way to do it than if you had more of a traditional relational type example. So here in event sourcing, this kind of gives us an idea of what something would look like. So we have this idea of we're going to order something, and this order happens to be order 1, 2, 3. So it's comprised of a bunch of different events. The first one is a card is created. The second event or command, which turns into an event, is item 1 is added for $30, item 2 is added for $15, item 3 is added for $12, item 4 is added for $5, and then shipping information is added. So these are individual contexts of behavior that are persisted to the storage mechanism, whatever the database is. In our case, it's Cassandra. Now we have something that transpires before the user clicks purchase. They decide to, or maybe even after they click purchase, they go back and they edit their order and they decide to remove item 2 that was $15. So it doesn't go to the database and delete that record. It simply adds a new event to the append-only storage, and that event is the context in which item 2 was removed. This becomes really, really important when you begin to think about auditing and asking or answering questions which have not yet been asked. And so in the shopping cart example, the idea is you have a manager comes back and says, look, our socks aren't selling well. We want to know why. It seems like we're guessing they're deleted before the customer presses purchase, or maybe they come back and edit their order. And if we have a traditional monolithic type system where we only store current state, we can't answer that question if we haven't added any kind of auditing. So we can say, okay, what we'll do is we'll add auditing. And so every time a record gets persisted to our relational database, we'll log the type of transaction it was. And then we can answer that question. So you go through a sprint, you add that to your system, boom, it works. And one of the drawbacks is from the point at which you deploy that to production, you can then begin to answer that question, but you can never answer it for orders that have already occurred. In an event sourcing system, that's not the case. You could go back to the inception or the beginning of when the application was first deployed, and you could answer that question because everything's stored as an event. So the canonical example we have here is a bank account. All of us have bank accounts, and we have debits and credits, and we have a check register, whether we do it online or do it by hand. And this image you see here is an example. We add $10,000, or we remove $4,000 with check 001. We do an ATM withdrawal, check 002 comes in. We do another deposit of $2,000. We have a balance of $7,992. Now, imagine if you're reconciling your bank account and you think you should have $7,000 plus dollars. You get your statement from the bank, and the bank says you only have $2,000. And you're saying, wait a second, this doesn't make any sense. You call the bank up, and the bank says, I'm sorry, we only store current state. So every time you do a debit or a credit, we don't actually store that transaction. We just update your current balance. Well, obviously that's absurd. That would never happen. But yet, in many of the systems we build, that's how we build them. We build them such that they only store current state, and we can't answer these types of questions. And so a lot of times in a more mature business model, such as accounting or the financial industry or energy or whatever, everything's stored this way, so we can answer those questions. Now, before we go any further, I just want to make one caveat. Not every system has to be event sourced. There are systems where current state current state is the only thing that matters, and history doesn't matter at all. But I think there's a fair amount of systems out there that do require historical data. And in fact, I would probably argue that there's more systems out there that require historical data or this event types approach rather than storing just current state. We've just been trained and have learned to think relationally as opposed to this style of programming. So, okay, so the idea is with these two components together, event sourcing and CQRS, you create a command and event classes. And in Akka and as well as Lagom, you're going to subclass something called persistent entity. And the persistent entity essentially gives you command and event handlers. If you read up on these types of programming models, they have these things called a command and event handlers. And essentially a command obviously is going to imperatively receive a request to do something. The command handler will then process it and validate it. If it's valid, it will then send it off to an event handler, which will then process it and persist it. And in Lagom, because it's built on top of Akka 2.4, you have clustering under the covers, and then you can access this from anywhere in the cluster. So that's really, really cool. And you can kind of think of this thing as the aggregate root and domain-driven design, if you're familiar with DDD. In fact, with Akka, Lagom, and these types of infrastructures, it's kind of moving to the quad D, distributed domain-driven design, which is an entirely different concept, a very fascinating topic to dig into. So some of the benefits of this approach, they allow you to time travel. And essentially you can go back in time and you can replay events, and you can, if you have data analytics plugged in, you could actually play around with, well, what would have happened if instead of this event being generated, that event was being generated? And there's all kinds of interesting things that you can learn and do. You can abstract over customer behavior and a lot of fascinating things. So the other thing it gives you is a natural audit log, which in a lot of industries is a requirement for security. Future business opportunities, as we discussed, the example of the shopping cart, it gives you the ability to answer questions that may not have been asked yet. You don't need a ORM. You get implicit read-write optimization, You don't ever need a database migration script. Yay. That in and of itself is pretty awesome because it's an event store, and regardless of what database you're using, it's going to look the same. Because it's an append-only storage mechanism, you're going to get performance and scalability out of the box, and testability and the ability to debug it. It's a pretty simple model to understand. You're basically recording events, and then you're going to play them back to derive current state. So before we go any further, I'm going to answer one of the questions that always gets asked. Okay, if you're recording all these events, that sounds like a lot of data, and you're storing a lot of stuff. That's very, very true. The question you have to ask yourself is how many events are you storing? It's not uncommon to store tens of thousands or even hundreds of thousands of events and just replay them. That's very easy. But there are systems that store tens of millions or hundreds of millions of events. And in those scenarios, or even maybe in the tens of thousands, you have the notion of snapshotting. So essentially, you're going to snapshot the current state of your entity. And then when you go to replay, in the event of failure or in scaling, the mechanism will replay back to the last known good snapshot. It will construct the entity off of that snapshot, and then it will play all the events from that point in time forward. And that's the way Akka-Persistence works, and Lagom uses Akka-Persistence on the covers. So the purpose behind that is to provide optimization for recovery. So you could snapshot every 5 events. You can snapshot whenever you want to. So it's when you snapshot is driven by your use case, essentially. So we'll go in here and we're going to add a friend. So we have an example out there called the Chirper. It's kind of like Twitter, if you will. It's a chat app, and we're going to add friend functionality to it. So in order to do this, we're going to create an add friend command class, a friend added event class. So you'll notice the way they're described there. Add friend, verb, noun, friend added, noun, verb, but the verb is past tense. And then you're going to define a friend entity who's going to hold state. And you're going to create a command handler and an event handler. So the first thing is to create the add friend command class. So the add friend command class, you're going to have an interface. It's going to be immutable. One of the things that we didn't talk about is immutable messaging. So the idea behind it is you don't want anybody mutating your message. If you think of the post office, when you deliver an email to the post office, it's in theory immutable. It's against the law, at least in the States, for anybody to touch, open, or in any way modify that mail once it enters your mailbox. At that point, it's supposed to be guaranteed to not be messed with. And so what that means is the person receiving the message receives the message that the sender sent. And that same idea applies to in distributed computing as well. So in this particular example, because we're using Java, it's a little bit more difficult. You have to implement equals, hash code, toString, etc., because you want to make sure that when this class is compared to ensure that it's the same, that it's a true check. So in this case, we have persistent entity dot reply type. We have friend command, add friend is the idea. Friend command is kind of like the root command class. It's going to have an ID, and then you're going to have a method called add friend, which is going to take in your friend's ID. And here you'll see preconditions, check, not null. So there's the idea you can, it depends on what your approach is to validation. Some folks believe that you should not even be able to create the class if you create it incorrectly. Other folks believe that it's okay to create it erroneously, but it will be caught by the validation handler. So either way is fine. In this example, we won't let you create it if it's created incorrectly. So the next thing is we're going to create the event class. And again, it's going to be immutable. And essentially, it's going to have a method friend added, which is going to take in the user ID of the user that's adding the friend, and then it's going to take in a friend that's being added, and it's going to have an optional timestamp. So we have, again, the checks here: preconditions not null for user ID, friend ID, and then timestamp. If it does not exist, then it's going to set it to be now. And again, you have to have the equals hash code 2 strings. If you're writing with the Scala API, if you're used to Scala or whatever, you have case classes and a lot of that boilerplate type stuff that we have to add in Java, you don't need to add in Scala. So now you're going to create the entity that's going to hold the state. And one of the things about entities in both Akka-Persistence and in Lagom is you kind of have an in-memory cache of current state. So there's a lot of things you get with these types of architectures that you don't get with other types of architectures. So caching comes kind of implicit in your structure. So here we have our entity, and you can see the types of commands and events that it handles. And it also has friend state, and its initial behavior essentially is going to be empty. So the state, when this entity first gets initialized, is obviously going to be entity. It's new. Now we have where we're actually going to add the friend. And so the idea is here is if the user is present. If the user is not present, meaning that the user does not exist, and for some reason this entity receives a request to add a friend to a user that does not exist, then we're going to throw an exception. Otherwise, we're going to create and we're going to find the user, and we're going to find the user's friends list, and we're going to add that user to the friend. And then we're going to return the state, which is the construct which holds the current state or the in-memory state for this particular entity. And we're essentially going to return an option of a new user. So essentially it's a defensive copy is the idea. So everything's immutable. We don't return anything that somebody could erroneously mutate outside of our structure. And all this stuff becomes very important because mutable state is okay if it's safe, if it's safe within a particular thread. But once you get outside of that, what we call shared mutable state is really bad. That's a no-go. So we basically do defensive copies of everything and so forth. And that way we ensure that everything is as it should be. And again, you have a hash code equals to, etc. Now we're going to create the command handler and the event handler. So now we have the command handler. Essentially, the command is going to come in. And again, this is part of our friend entity. All this is in the same class. And the command will come in, and if the state of the user is present, or if it's not present, then we're going to throw an error because the user had not been created yet. If it is present, then we're going to get it, and we're going to see if it contains that friend already. If that friend does already exist, then we're not going to add it because the friend already exists, and we're just going to return the current context because this friend that you're trying to add has already been added. Or we're going to add the friend, and we're going to create, you'll see there, context.then persist. We're actually going to persist the event. And then you'll see the partial function there completes with a reply. So it's going to basically reply with done. And then finally, we're going to create the event handler. And the event handler is real simple. It's essentially saying state.addFriend. So as a side effect of persisting the event, you're going to update current state. And in this particular one, there are no side effects, as you're just updating the state. After you've updated your state in an event handler, you might side effect by perhaps sending a message somewhere else or whatever. But in this particular example, you don't. So the key is that when the partial function or the persist partial function completes, you then now have a guarantee that your event has been persisted to the database. And so then you can go ahead and update current state. You don't want to update your current state until you know that your event has been persisted. So, all right, and then finally we're going to implement the service call, and we simply go back to our descriptor, and we add in our interface the route, and we add the function or the method that we just created, add friend. And then we go into the implementation, and we add the additional code that's required to add that. So we see we added persistent entity registry, and we see down there to the service call add friend, we're essentially going to return an entity ref, and we're going to do an ask. And an ask is a succinct way to do essentially it's a future and a promise combined in Akka that give you the ability to provide a callback. And once that completes, then you're going to reply back to the caller. And then you'll see the additional friend entity ref there, which essentially is going to, underneath the covers, access the persistent entities and allow you to persist that event should it pass validation. So what we just went through was the notion or the implementation or how a developer would implement event sourcing and CQRS inside of Lagom, and that's the default standard. So if you're going to use the persistence mechanism out of the box that Lagom provides you, then that's the way you would do it. You can do CRUD-based persistence in Lagom. There's just no infrastructure for it. So you would have to do it all yourself. You'd have to write your own code for it or use an ORM or something like that if you wanted to. It is possible, but there's no built-in API for it. That most likely will change in the future, but as to when, I cannot say. So the other thing that you get is tight integration with Cassandra, and it creates the query tables, and you also have something called the Cassandra Reside Processor, and it's a real nice class which essentially sits on top of Akka Query and consumes events that are produced by a persistent entity, and then it will update Cassandra tables that are optimized for querying. So there are different tables. You have the persistent store entity table, which stores the events, and then you'll have these other tables in Cassandra, which essentially are optimized for querying. And then you can use the Cassandra query language, and here's an example: select ID title from, post summary, etc. So these features are baked into the structure of Lagom. So running in production, our next topic is we have SBT native packager, which is built in, and so you have the ability to produce zip files, Microsoft files, RPMs, Docker-based files, etc. It also plugs into Conductor, which is our orchestration tool for container, and the latter two, Conductor and the reactive platform, are what's going to be called our production suite, which will be Conductor and monitoring, are subscription-based services. And with that, you would get Conductor, you would get split brain resolver for Akka cluster. If you're not familiar with that, clusters can essentially encounter a scenario where they have a split brain. And the idea, one of the challenge in distributed computing is just because someone doesn't answer you doesn't mean they're down, right? So the example is if I send you an email and you don't respond to me, say within 5 minutes. That doesn't mean that you died or that you no longer have that email account. You know, you could be out getting a cup of coffee, you could be sleeping, who knows? You'll eventually respond to me. So in a distributed system, we don't truly know if another system is down or if it's just not responding due to latency. So what ends up happening is sometimes the cluster management tools will assume something's down and they'll break off from the cluster, and you end up getting 2 clusters rather than 1. And that's called split brain. And so we provide a resolver that will help reconcile that. And then, of course, Lightbend monitoring. The challenge is that most monitoring tools today don't know how to deal with message-driven systems like Akka, which Lagom is under the covers. And so we provide a solution which addresses that and deals specifically around actors, and Lagom too. Lagom implements circuit breakers for service management, and so we monitor those as well. So you can use Conductor, you can use a split brain resolver, you can use Lightbend monitoring in development, but once you get a production, you have to get a subscription. The nice thing is our subscription includes all of it, so you don't have to piecemeal it together. So our current version was just released, not yesterday. It was actually released 2 months ago. Let's see, what is today? September, yeah, 2 months ago, 1.0. And I think it's actually been updated since then. There is obviously the first release included Java API, and I know the Scala API exists. We actually did some presentations at Scala Days New York with it, and it works quite well. I'm not sure if it's been released yet or not. I'd have to double check on that, but in any case, it is there. And some of the things that we're working on for the future of Lagom is Maven support, which I've seen, I believe is in pre-release or is going to be released here shortly. Integration between intra-service communication via Kafka instead of REST, or I should say in addition to REST. Obviously the API, the Scala API, and other orchestration tools support, such as potentially Kubernetes and so forth. And then Swagger integration and a more succinct, or really an API period for integration tests, where you can write tests that cross microservices. And these can become quite complex because you have to spin up multiple JVMs, etc. Akka has this with the multi-JVM support, so it will be coming to Lagom as well. That's pretty much wraps up my presentation tonight. So I would encourage you to check Lagom out, check it out on GitHub. Go read the documentation. It's really good. Jonas wrote a Reactive Services Architecture book, which is excellent, which kind of pulls together the notion of reactive computing and microservice-based architectures. And Greg Young has a presentation on Eventsource, which is really, really good. I'll post these slides to the meetup so you guys have access to them, and give you a link and so forth. And O'Reilly has 2 books on this topic. One is written by Jonas, which is the one that I mentioned in the previous slide, and another one written by Marcus is Developing Reactive Microservices. So both of those should still be free, and there's links there to them as well. So at this point, that wraps up our presentation. And again, I kind of addressed the CRUD versus event sourcing question already. Another one is push versus pull. And this is an interesting question. And this is one of those questions you waver back and forth. Should I push out to loosely coupled environments, or should I let them pull from me? It depends. I think there's times when push makes sense. I think there's times when pull makes sense. I think there's an implicit security benefit to a push model in that nobody ever goes into your DMZ and pulls out data. You're always pushing it out. So there's some advantages there, but there are some questions. Pull is more centralized, push is more decentralized. It's a tough question to answer. I kind of favor push, but there are scenarios where pull makes sense. And the serverless, the whole serverless thing that's coming out now, there's some interesting ideas here. So essentially the idea is you're going to go even further than a microservice. You're going to go down to, you want to call it nano service or whatever, basically like Lambdas and Amazon functions. And I think there's a level of decomposition where you start to lose a context of what you're trying to build. So, a microservice can be as small or as big as you want to make it. And Lagom is no different. You can make a microservice just be one method call if you want, or you can make it be a whole bunch of method calls. That's one of the nice things about Lagom. It doesn't, while it's opinionated and will say this is how you should build it, you still have complete control over what you build. And so if you want to really go down to the function level, so to speak, you can do one method on each microservice. I don't necessarily recommend that, but you can do that kind of thing. So yeah, so I think that's it. If there's any questions, I don't know if we have a forum to answer questions, but that's pretty much the presentation, and I appreciate your time, and I'll turn it back over to Edu.
Okay, thank you, Duncan. Let me ask if there are any questions, please. Hi, Duncan. No, at this moment, there are no questions from the people here. So I think that that's everything. So thank you so much for your time.
You're quite welcome. And should any questions arise, you can go ahead and email me, Edu, and I'll do my best to answer them. But I appreciate it, and I hope everyone is doing well tonight. And it was great to join your meetup and talk about Lagom.
Okay, thank you. So that's everything.
Okay, take care.
Bye, Duncan. Take care.
Bye-bye.